Alright, so in this video, we're going to be solving the problem, LeetCode Hard Problem number 2603, which is collect coins in a tree. So let me go over the problem statement once, and then I'll go over to the examples. So firstly, we've been given an undirected and unrooted tree with n nodes indexed from 0 to n minus 1. We're given an integer n and a 2D integer array, edges of length n minus 1, where edges of I is equal to ai comma bi, which indicates that there's an edge between nodes ai and bi in the tree. You're also given an array coins of size n, where coins of I can be either 0 or 1, which in which 1 indicates the presence of a coin in the vertex I, and 0 means no coin is present on that vertex or on that node. So initially you choose to start at any vertex in the tree. Then you can perform the following operations any number of times. Collect all coins that are at a distance of at most 2 from the current vertex, or move to any adjacent vertex in the tree. So we choose to start in any vertex, and we can either collect all the coins that are at a distance of at most 2 from the current vertex, or move to any adjacent vertex in the tree. So our aim is to find the minimum number of edges we need to go through to collect all the coins and go back to the initial vertex. So our aim is to find the number of edges that we go through to collect all the coins that have been spread out in our tree, as well as come back after collecting all the coins, come back to the initial vertex where you started. So that is the aim, and we need to do this in the most optimal way, that is by taking the most minimum steps, right? So the minimum number is also minimum is also a keyword here. Note that if you pass an edge several times, you need to count it into the answer several times, right? So let us take this as an example. This is our first example. So this is the graph that is formed here. It is undirected and unweighted, and also unrooted. There is no root. So let us say we start at vertex 2. Firstly, our input is given. Coins would be present at the 0th index and the 5th index. As you can see, this is the 5th index, and this is the 0th index. So the coins are being present here. That's why it has been marked with a bold outline, and the others have no coins present, right? So we can start at vertex 2, collect the coin at vertex 0. Now move to vertex 3 and collect the coin at vertex 5, then move back to vertex 2, so it takes total 2 moves. The question mentioned that we can start at any vertex, and from that particular vertex, we can either move to another vertex which is adjacent to it, or collect the coins which are at distance 2. So if you see, there are 2 edges between 0 and 2. So you can see that we can collect the coin from here without having to move to any adjacent vertex. So one step, we haven't performed any step right now. We are standing here, we have just collected this coin, and in order to get to this, since you see the distance is equal to 3, 1, 2 and 3, so we would have to move to the adjacent vertex. So now once we are at 3, we can collect the coin at node 5. So we collected this and mark it as 0, and then we also it is mentioned in the question that we have to return to the initial node that we have started from. So then we return to it. So you see the steps are 1 plus 1, one from going to 2 to 3, and the other just for coming back from 3 to 2 after we have collected all the coins in the tree. So the answer is 2, and that is the minimum number of moves, right? That's one example. Then another example could be this one, where we have been assigned this, and the coins have been placed on the nodes 3, 4 and 7. So the most optimal way, let us say we start at vertex 0 that is present here, and we need to collect the coins at vertices 4 and 3. So you see that the distance between 0 and 4 and 0 and 3 is equal to 2. So we don't have to move at all. We can just collect these 2 coins, mark them as 0, that is, these have been collected, and then move to node 2 with one move. And then you see the distance from 2 to 7 is also 2. So we collect this coin as well. Once we have collected this coin, we have to finally move back to 0 since we have collected all coins. So that also takes 2 steps, right? So I hope the problem is clear. The problem statement is clear. So what we need to do, let us just go over how we need to perform this. Let us go over the hints. So all leaves that do not have a coin are redundant and can be deleted from the tree. So here you saw an example that, okay, so how do we traverse a tree? It's either via BFS or DFS, right? Now we have some redundant nodes which can cause TLE as well. For example, the node 6. Now this is a leaf node and this does not have any coins on it. So we can easily just remove this node and perform a BFS on the remaining part, right? So that's our hint 1. That is all leaves that do not have a coin are redundant and we can delete them without a second thought, right? Then our hint 2 is that we remove the leaves that do not have coins on them so that the resulting tree will have a coin on every leaf. We remove the leaves that do not have coins on them so that resulting tree will have a coin on every leaf. This is also practical advice that if you remove this leaf, then all the leaves in the tree you can see have a coin on them, right? So that's hint 2. And hint 3 is finally, in the remaining tree, remove each leaf node and its parent from the tree. The remaining nodes in the tree are the ones that must be visited. Hence the answer is equal to remaining number of nodes minus 1 times 2. So I'll explain this. Let me just get to the coding part of this problem. So I'll explain to you how we are performing this, right? So firstly, this is basically, as I was saying, we first just do the, steps of creating the graph, that is the adjacency list. So this is the adjacency list representation. And then we also maintain a degree that would basically be storing the value of the number of edges being connected to that node. So degrees of each node we have appended into this vector of int type. Now we basically take a queue. Okay, so the queue basically our aim is to traverse the graph, right? So I'm taking a queue to perform BFS. So this queue is for the leaf nodes which can be removed. And basically in this problem, what we have to do is we have to keep track of the leaf nodes and remove those leaf nodes which have no coins. So this is a queue for leaf nodes which can be removed, which means that if the degree of the node, we traverse through each node, if the degree of the node is 1, that means the node is a leaf node and the coins of that node are 0. That means that it is a leaf node with no coin. We are going to be deleting those leaves that do not have any coin, right? As in this example, 6 is a leaf, so the degree of 6 is 1, right? And the coins on 6 have been marked as 0. So this is basically we're going to just push it into the queue, since we're going to be removing this leaf nodes, each element from this leaf nodes queue, right? And we maintain a basically removed vector which would be storing whether the node has been uh, whether the node has to be removed or not. So vector of bool removed, and we initialize all with false. Now we start our BFS, that is while the queue is not empty, int node is equal to q.front and q.pop, which is the standard template. And then we also mark removed of node is equal to true. That is this node, now since we have visited it, it would be marked as true. And this would be storing the leaf nodes which have no coins, right? Now reduce the degree of the neighbors and check if they have become new useless leaves. So for each neighbor of those leaf nodes, when we remove the leaf node with no coins, in case that node has become a useless leaf, that is if in case that node does not have a coin, then we have to remove that as well. So basically we push that into the queue. That means that this neighbor is also going to be removed. So this means that if neighbor becomes a leaf and has no coin, remove that too, right? So that's why we are pushing that into the queue, because this queue maintains the leaf nodes that have to be removed, right? And finally we see that uh, we will just remove all those nodes which are redundant, which are leaf nodes that have no coins on them. Now, since coins within distance equal to 2 can be collected from a particular node, we don't need to walk to the leaf coins. So if the distance, as I had explained, that if the distance is equal to 2 from 0 to 4 or 0 to 3, you can see, if the distance is equal to 2, then we do not need to perform any steps. So that is why we have taken a step value of, basically step value is 1 only, but if the step is less than 2, that is if the distance is less than 2, less than or equal to 2, so that is why we're starting from 0. We maintain another queue and we go over all these nodes and we check if the leaf has no coin. If this so this means degree of the node is 1, means that it is a leaf. And if it is not coming in the removed vector, that means that this node does not have to be removed. That means that it has a coin already. So if that has a coin, we will push it into the q2 and now perform a second BFS. This is the code for second BFS here. So while q2 is not empty, again we pop out the node and store it into this variable node, and we mark it again because now the leaf node which has a coin has already been visited. So we have accumulated that coin, right? And we mark the removed node. Then we go over to the neighbors of those nodes and check if the neighbor has not yet been removed. Then only we decrease the degree of the neighbor. That is, if it has not yet been removed, we have to make sure that we remove it for us to basically move forward, right? And finally, remaining nodes is equal to 0. We create a variable to basically calculate the remaining nodes in the tree. And for each of the node we traverse that is remaining in the tree, if it has not been removed, that means that we will increase the counter of removed nodes. And finally, we're going to be using this function, that is remaining nodes minus 1 times 2. So this basically means that remaining node basically is going to store the number of steps that we are 1 plus the number of steps that we are moving to. So removing rem nodes basically means that if we are moving from here to here and here back, so this value is actually rem nodes minus 1. And we are doing a multiplication of 2 since we also need to come back to the node. Since this has not been accounted for, we have to come back to the node, right? So that is why we have multiplied it with 2. And rem nodes minus 1, we have done that to basically get the first traversal. And coming back is times 2. And we return max because we don't need a negative answer. So max of 0 with that. And let me just submit it for you to show you whether it's getting accepted or not. And yeah, it has been accepted. So yeah, that's it about the problem.